Okay, so we left off last class talking about Hamilton's method. And if you remember, we calculated every player's exact fair share, right, of the seats in Congress or of the candy or of whatever we're doling out. And then we rounded everybody's down. So we just cut off the decimals, rounded them down. And then we gave out the extra seats to whoever had the largest fractional piece. Like we looked at the decimal pieces and gave out the extra seats to the largest decimal. And this seemed like a really good, pretty fair system. It's easy to explain, quick, and fair. So these were all good pros that we talked about. So of course, though, it's got to have some cons. Otherwise, we'd still be using it as our method of apportionment today, but we don't. So we're going to do a few examples that demonstrate each of these three serious drawbacks to Hamilton's method. So here's our first one. We have a small country, has 3 states, Bama, Tecos, and Illinois. Has a total population of 20,000 people, 200 seats in the House of Representatives. We want to determine the apportionment of the 200 seats under Hamilton's method. So I want you to work in your groups. Remind yourselves how to do Hamilton's method. Come up with the apportionment. How are we going to give out these seats in Congress? Okay, so let's go over this initial one here. So my standard quota, there were 3 methods for calculating it. You can use a proportion, you can use percentages, or you can use a standard divisor. I'm going to do the standard divisor method just to remind you of it because I'm going to need it later on in this class. Okay, so the way we do that, pull out my calculator. Okay, so you do your total population of 20,000 people and you divide by the number of seats, 200. That gives you something called the standard divisor, which represents the number of people per seat. That's the number of people that each congressperson represents. Okay. 100 people. So then you have to figure out how many sets of 100 each state has. How many sets of 100 people are in each state? So you do each population divided by 100. So if I do 940 divided by 100, we get 9.4. 9,030 divided by 100 is 90.3. 10,030 divided by 100 is 100.3. When you add these up, you get exactly 200 seats. Okay. Problem is we can't give out a piece of a seat. You can't give someone 9.4 seats in Congress. So we're going to round them all down to get the lower quota. So we're going to have 9, 90, and 100. But when I do that and add them up, I've only given out 199 seats. I have 1 extra seat. Who am I going to give it to? Bama. They get the surplus because they have the largest decimal piece. Right? They are the closest to getting 1 other seat based on their population size. So I give it to Bama. So my final apportionment is going to be 10 for Bama, 90 for Tecos, and 100 for Illinois, and that gives me my final 200. 10, 90, 100. So now I'm going to do this same apportionment, except imagine that overnight the number of seats is increased to 201. Okay? And this happens, like in our own House of Representatives, the number of seats in the House of Representatives changes over time. As the country grows, we might add more seats, something like that. So we're adding a seat to our Congress, 201. Nothing else changes, no population changes. So I have to calculate a new standard divisor. I do my 20,000, and this time I'm going to divide by 201 seats. So my standard divisor is 99.5 something, something, something. So I'm going to divide each population by this much instead of by 100. So a nice little trick is to have your calculator remember this number instead of having to type in the decimal over and over. So if you have a standard little calculator like this, there's usually an M+ button, which means memory. Add it to the memory. And if you have a graphing calculator or a more fancy scientific calculator, there's usually a store button, like STO for store. You can use that. So now I'm going to do 940 divided by, and then when I want the number back, I press MR for memory recall. So I have 9.447. Okay, and then I'm going to do 9,030 divided by that 99.5 number, and I get 90.7515. Then 10,030, 100.8015. So when I add these three up, I'm going to get a total of 200. Get exact, oh, sorry, 201. There's 201 seats now. So I can't give part of a seat, so I chop off the decimal parts and I just give everyone the whole number of seats that they deserve. We have 9, 90, and 100. So how many seats have I given out total? 199, which means how many surplus do I have? 2, because I'm giving out 201. So who gets them? Tecos and Ilnos. They have the largest decimal pieces. So my final apportionment is going to be 9, 91, 101 for a total of 201 seats. So what do you think? In the previous apportionment, that one was 10, 90, 100. So it was 10, 90, 100. And now it's 9, 91, 101. I moved this. 9, 91, 101. Are any of the states really upset about this? Bama. Bama had 10 seats out of 200 to give out. And we had 200 really precious, valuable things to dole out among 3 states. Bama had 10 of them. And then someone says, good news, everybody. We have 201 of those precious, valuable things. We have more things to give out now. We redistribute them, and now Bama has less. We added the really great, precious seats in Congress. There are more of them to give out, and Bama lost one. That's kind of weird, right? So the other 2 states each picked up one, and we took one away from Bama. So what we just saw, that's called the Alabama paradox. And it happens when an increase of the number of seats to be apportioned causes a state to lose a seat. The name of it comes from the 1882 apportionment of the House of Representatives. And this is what was being debated. So there's a little table here. We had Alabama, Texas, and Illinois, like Bama, Tecos, and Ilnos, right? So we did an apportionment with 299 seats and then an apportionment with 300 seats. When there were only 299 seats to give out, Alabama got 8 of them. And then when we increased it to 300 seats, there's one more seat to give out. We took one away from Alabama and increased both Texas and Illinois by 1. It doesn't make sense. That's why we call it a paradox. Yeah, so we call it the Alabama paradox. It doesn't make sense. We have more things to give away. How am I losing, right? If I'm Alabama, with 299 seats, I had 8 seats for Alabama. Then we increased it to 300. There are more things to give away. How am I losing a seat? Right? So this is like a little quirk or paradox of Hamilton's method. Big drawback of Hamilton's method, because the size of the House of Representatives does change, right? So this is something that can happen and has happened. Okay, but it's not the only drawback of Hamilton's method. Here's another example that will show us another one. So here we have 5 planets in the Utopia galaxy signed a peace treaty. They agreed to form an intergalactic federation governed by an intergalactic Congress that has 50 seats in it. So this is the story of the 2 apportionments that broke up the federation. So first, in your groups, I want you to use Hamilton's method to apportion the 50 seats to the 5 galaxies, or whatever they are. Okay, so finish up. Go ahead and finish up, but I put the final apportionment up so you can check your work when you're done. 8, 4, 10, 11, 17. And once you have that, I want you to move on to the next part of the question, where some of the populations change. Okay, so the final apportionment after 10 years with some small population changes gives 8, 5, 10, 11, 16. So it was 8, 4, 10, 11, 17. And now it's 8, 5, 10, 11, 16. So the change is that planet B here got another seat and planet E lost one. So E gave one to B. Now B's population was 78 and it stayed 78. So the population of planet Beta stayed exactly the same, yet they got another seat. Seem okay? No. In the second one, we just had 1 to give away. Yeah.
So how did that one get 5 and that one also get 10? It would have got 9 and 4.
Okay, well, let's do the whole thing out.
Which one are you talking about?
The second one.
Yeah, we got two.
After 10 years?
So my total population is 909, right?
Yeah. Divided by 15 is 18.8.
Divided by 50, 18.18.
Yeah.
Okay, so I'm going to do each population divided by that. So I have, that's wrong, 150 divided by.
My memory button.
Yeah, okay. Oh, I have to do memory clear first. Okay. $150 divided by, so I get 8.25. Okay. 4.29. So that should add up exactly to our 50. The lower quotas are going to be 8, 4, 9, 11, and 16, which comes to 49. Okay, yeah, 8 plus 4 is 12, plus 9 is 21, 32, yeah, 48, okay. So I have 2 to give out, so I'm going to give 1 to, yeah, Beta and Coney. So yeah, so I have 5 for Beta, 10 for Coney, and everyone else gets their lower quota. 8, 5, 10, 11, 16. So let's look at Beta, and the only ones who changed are Beta and Elysium. Okay, they got their apportionment changed. So Beta went from 4 to 5, Elysium went from 17 to 16. So let's look at their populations. Let's look at B and E. Population 1, population 2. This is a bad chart. Hang on. Okay, so for beta, their population was 78, and their apportionment was 4 seats. First time around. Second time around, their population was still 78, and their apportionment was 5 seats. They have nothing to complain about, right? They got an extra seat. This is a little weird, but nothing to make them upset, right? In fact, they're probably pretty happy about this. But when we look at Elysium, their population went from 295 to 296. So 295 to 296. So their population grew. Their population grew. But their apportionment went from 17 to 16. So Planet Elysium is going to be really upset about this. Okay. Their population got bigger, but they lost a seat. So they have more people and less representation. This is called the population paradox. It happens when a state's population goes up, but the number of seats it's apportioned goes down.
But we need to know that vocabulary.
Yes.
So
Yep.
we're going to go over what we're going to do.
Yep. So this is the population paradox. When a state's population goes up, the number of seats it's apportioned goes down. This is a major flaw, right? This is something that we would not want to happen in a good apportionment method. Seems as though if you get more people, you should have at least the same, if not more, seats. All right. That's 2 major drawbacks to Hamilton's method. There is one more. We'll see from this example. Okay, so for a change of pace, we're going to use a non-political apportionment problem. We're going to use garbage trucks. Okay. So you have a garbage company. It serves Northtown and Southtown. Northtown has 10,450 homes, and Southtown has 89,550 homes. So altogether, how many homes does this company service? 100,000 homes. They have 100 garbage trucks. Okay, so I want you to apportion the trucks, right? How many trucks do they send to Northtown and how many trucks do they send to Southtown using Hamilton's method? Okay, so let's discuss. If there are 100,000 homes and 100 garbage trucks, how many homes per truck? Home? 1,000? 100,000 homes, right? There are 100,000 homes. Divided by 100 trucks is 1,000 homes. So each truck is responsible for 1,000 homes. So then we have to figure out how many sets of 1,000 homes there are in each district. So you divide the number of homes, 10,450 by 1,000, 10.45. And this one would be 89.55 for a total of 100. Okay. Then Hamilton's method says round down, so we have 10, 89, but that's only 99 trucks, right? Who gets the extra truck? Southtown, because they're the closest to being at 90. The decimal part is the biggest. So they get the surplus, 90, 10 trucks to Northtown, 90 trucks to Southtown. Seems like a reasonable way to apportion. Now, the garbage company has been hired by Newtown that has 5,250 homes. So because they have already figured out that they have 5 trucks. They have 1 truck per 1,000 homes. They're going to buy 5 new trucks to service this new town, so that the service to the other 2 towns won't be affected. So let's carry out Hamilton's method with the addition of the 5 additional trucks. All right, let's go through it. So I now have 105 trucks to give out because the company bought 5 new trucks. They had 100, they bought 5 new trucks, so I have 105 trucks to apportion. So I'm going to take my total population, 105,250, that's how many homes I have, and I want to give out 105 trucks. So that's 1,002.38 homes per truck. So each truck is going to service 1,002.38 homes. So save that number. What's that? Oh, yeah. Okay, so now I'm going to take each town's population, and I need to know how many sets of 1,002 are in there. That's how many trucks they get. So I'm going to do 10,450 divided by 1,002, and I get 10.425. And then 89,550. 89.337. And then Newtown, 5,250. 5.237. So when I add those up, I should get 105 trucks. Add up all those exact values, I get 105 trucks. Lower quota round down, so I have 10, 89, and 5. But that only adds up to 104. So I have 1 truck to give out. Who's going to get it? Northtown, 0.425 is the largest decimal. So my final apportionment is going to be 11, 89, 5 for a total of 105 trucks. So this, what do you think of this? Is there anything weird about this? Yeah, Southtown might not like that they're not good. If this company takes on Newtown as part of its service, Southtown's going to get gypped. Oh, they have the biggest population. So Southtown's getting gypped of a truck. So this didn't affect Newtown. We bought 5 new trucks, right? We bought 5 new trucks to service Newtown. That's exactly what Newtown ended up with, 5 new trucks, right? But so why would I take a truck from Southtown and give it to Northtown? That just seems weird. I already had them perfectly apportioned at 10 and 90. I have 5 new trucks now. Give those to Newtown. And then I just swapped. I said, instead of 10 and 90, we'll do 11 and 89 and make Southtown mad. It is silly. It's weird. So this is called the new states paradox. So in this case, we added a new town, right, as opposed to a new state, but it's called the new states paradox. It happens when the addition of a new state with its fair share of seats affects the apportionment of other states. So here, we added a new town, we gave them their fair share of trucks, and yet we messed with the apportionment of the other 2 towns when it should have really just stayed the same. So that's called the new states paradox. So we have all these really serious flaws for Hamilton's method. It looked really great at first, but then you dig a little deeper, we found all these really serious flaws. So another founding father. Okay. So remember that in Hamilton's method, we divided every state's population by the standard divisor and rounded the result down. So up until now, things are pretty fair, right? Up until right then, we've done the same thing for everyone. it's when we start deciding who gets the surplus seats that things go a little wonky, right? That's when things get weird. We start giving out the extra seats. Sometimes you get it, sometimes the other state gets it, and it makes people upset. So Jefferson's idea said, instead of dividing by the standard divisor, let's tweak the divisor. We're going to change the divisor so that once we round everything down, there will be no surplus seats. Okay, so we're going to change the number we divide by to try to make it so that after we round down, there are no surplus. All right, so to make this idea work, we have to think about division. If we want the quotas to be do we want the quotas to be a little bigger or a little smaller? Bigger, because we want there to be no leftovers. So I want them to, after I round them down, be big enough so that they add up to the total instead of being too small. Hang on. Just wait. So we need the quotas to be a little bit bigger. So how should I change the divisor? If you want the answer to a division question to be bigger, what are you going to do to the number you're dividing by? Smaller. I have to make the standard divisor, the thing I'm dividing by, smaller. So let me just write it out right? If I want C to be bigger, I want the answer to my division question to be bigger, then I have to make this number that's going into A smaller. Okay. So that it will go in more times. If that makes it clearer. B will go into A more times if you make B a smaller number. Okay, so let's revisit the Parador Congress. This was our first example that we did with Hamilton's method. This time we're going to use Jefferson's method to apportion the seats. So I already have the standard quotas, right? And I got them with a standard divisor of 50,000. So if you remember there, I was giving out 250 seats. I was apportioning 250 seats. So I took the total population, 12,500,000, divided by 250 seats, and I got 50,000 people per seat. Okay, so I divided each state's population by 50,000. Okay. When I round them all down, I get 32, 138, 3, 41, 13, and 19. And you come up with 246. So we have 4 extra seats. So we said, all right, this is too small. I need this sum to be bigger. So I'm going to make my divisor, the 50,000, smaller. Okay, so that all my answers will be a little bit bigger. So instead of dividing each population by 50,000, let's try 49,500. So I'm going to divide each state population by 49,500. And I'm going to call the answer a modified quota. So pull up my calculator. All right, 1,646,000. Instead of dividing by 50,000 people per seat, we're going to divide by 49,500. Something a little bit smaller. Yeah, I'll tell you exactly how to change it in a minute. So I change it to something a little bit smaller. And that makes my answer come out a little bit bigger. So I get 33.25. So you see, last time I got 32.92. Now I have 33.25. So I made the answer a little bit bigger. That was my goal. That way, hopefully, after I round down and add them up, I won't be short seats. All right, so let's do 6,936 divided by 49,500, and I get 140.12. And 154,000 divided by 49,500, 3.11. Repeating, yep. and 2,091,000 divided by 49,500, 42.24. $685,000 divided by 49,500, 13.83. And 988 divided by 19.96. Now, when I add those up, I'm not gonna, that actually doesn't make any sense to add them up, okay? So don't worry about that. Now I'm gonna round them all down, so I get 33, 140, 3, 42, 13, and 19. And when I add those all up, I get 250. 49,500. Totally randomly for now. I just said I need something a little smaller than 50,000, and I guessed. I'll give you a way to guess in a minute.
13.83. Why would you round down the 83?
Because you always round down in this method. We always round down, no matter what the decimal part.
So are we gonna have to figure out?
Yes. You're going to have to figure out the number D. The 49,500, you're going to have to figure it out. But the magic is now there's nothing left over. So I don't have to decide who gets extras. Okay. Yeah. So the summary of Jefferson's method is find a suitable divisor D. Okay, that was 49,500 in our example. Using D as a divisor, compute each state's modified quota, that is, do their population divided by D, and then give each state its lower quota. Round those numbers down, and that's how many seats they get. The hard part of this method is step 1, right? Finding a D. So you have a little flow chart that will help you find it. Use D, the standard divisor. Start with the standard divisor of 50,000, right? They round everything down, add the lower quotas up. We call that sum T. In our case, that was 246. Okay. And then you ask yourself, is that number equal to the number of seats in Congress? No, because there were 250, right? So you follow the flow chart to know. Is that seat too small? Is that number too small? Or is it too big? In our case, it was too small, right? We had 246, it was too small. So we go here, and it says make D smaller and start again. So it could be that we went down to 49,000. You have to just start with a guess, and you're going to do narrow in on a divisor that works.
Is that always gonna be like a round number, like 500, or could it be like 100 feet?
There's always going to be a range of numbers that will work. So you don't have to find like a single number. Yeah.
So like your so your 49,500 could be 49,501.
Yeah, that would also probably have worked. 49,600 might work. Yeah. I don't know. So in our case, the number was too small. We only had 246 seats, so we made D smaller, and it worked out perfectly. But if we made D smaller, too small, then the number of seats might come out too big, and then you have to make D bigger. And so you have to kind of narrow in on it. So let's just go through how we might have come up with that 49,500. Okay, so I start with my standard quotas. So this is always a good place to start. Just do the standard divisor of 50,000, just like you do with Hamilton's method. Round them all down. We have 32, 138, 3, 41, 13, and 19, and that only adds up to 246 seats. So I have too few seats. So according to my flow chart, if I have too few seats, make D smaller and start again. So my next step here is make D smaller. Too few seats make D smaller. So maybe I choose 49,000. I go, okay, 50,000 is too big, try 49,000. So now I have to do each population divided by 49,000. So 33.59.
So we're allowed to round.
Hmm?
Are we allowed to round?
I don't know what you're, okay. So 6,936 divided by 49,000. So now I have 141.55. And 54. So I have 3.14. And I get 42.67. And 13.98.
You rounded up there.
Yeah, but I'm not actually, the decimals aren't going to matter because I'm just going to round them all down. So yeah, I'm just keeping 2 decimals for now. So 20.16. Okay, so it doesn't, I don't have to actually calculate the total there. Round them down and I get 33, 141, 3, 42, 13, and 20, which is 252. Too many seats, right? So my next step, too many seats, is make D bigger. So now, you know that 50,000 is too big, right? 49,000 was too small, so you try something in between, 49,500. And we already did this, and we know that it comes out perfect. Okay. Yeah, 49,300 might work, 49,600 might work. Yep. There's always going to be a range of numbers that work. You're not looking for a single value, because that would take forever. Yeah. So under this method, right, which we have already done back here, take a look at state B. Look at its standard quota. That's the exact number of seats that it deserves. That's the fairest thing. If we could give a part of a seat, that's how much B should get, right? That's its exact fair share. Let's look at how many it got. Anybody see a problem?
That would make sense.
Yeah, so we talked about last class, we talked about something called the quota rule. We said it would make the most sense. Like this would be the perfect system. If you could give out part of a seat, this would be how we would do it. You just give out parts of a seat and this would be perfectly fair. But we said, but you can't give out part of a seat, and it only makes sense to be fair that if you can't get 138.72, your fair share should be 138 or 139, right? You either round it down or round it up. But they got 140.
So they rounded it up.
Yeah, so that is what we call a violation of the quota rule. So the standard quota was 138.72, I think. And then the final apportionment was 140 seats. This is a violation of the quota rule. We call it an upper quota violation because they got too many. They got more than their upper quota. So we have a flaw, right? Jefferson's method was great, but now we have a flaw. So it turns out Jefferson's method can sometimes produce upper quota violations. And even worse than sometimes doing that is that those violations consistently favor large states. So the states that end up getting more seats than they should are always the large ones. So this problem came to light in 1832. It was one of the most heated apportionment debates in U.S. history. And using Jefferson's method, New York's standard quota was 38.59, but they ended up getting 40 seats. Okay, this made a lot of other states really mad. They're getting more than their fair share. So that was the last year that Jefferson's method was used because people questioned its constitutionality. 2 new methods were proposed as alternatives, one by John Quincy Adams and one by Daniel Webster, and we will study those next class.